I need to press that I agree, yes. Okay. So I hope Dong would join us along the way. So, according to various desires, and I'd like to talk about. So let us see. Am I here? BCOV theories.
Mm-hmm.
So actually, I don't want to go too fast,
Mm-hmm.
right? So please ask me questions, and I will talk about three types of BCOV theories. First theory is the Hodge strings that I developed together with Sergei Shadrin. Second, it is BCOV theory itself. Like it was defined by authors.
They also called it Kadir-Spencer gravity or something like that, right?
Yes, but mostly it is known, the authors called it like this, but mostly it is known as BCOV. And the third theory is a version of this theory that comes from the tropicalization of a model. And I want to go this slowly such that you would be able to understand. Okay? Every bit. Right, Pasha?
Yes, please.
Okay. So I start with number one. So first, motivation. Motivation is like this. Suppose we have kind of a string theory. In string theory, we have an integral over MGN. It doesn't look like a field theory. However, so here we have some measure. However, imagine that this measure can depend on some parameters. I don't know, lambda. Then imagine that when lambda going to some lambda critical, the support of omega of lambda is going to the neighborhood of the degenerated surfaces. So degenerated surfaces are, of course, mostly look like this. So they're just trivalent graphs, trivalent vertices, joined by cylinders. So this integral over moduli would correspond to integral over the moduli of cylinders. It contains length t and also angle phi. And we assume here that this is irrelevant parameter. So it means that original integral does not depend on this parameter. So how could it be? It could be because we have Q symmetry here, and these deformations are exact. Okay. So we need to study two things separately. One thing is the cylinder itself. So since we are doing the string theory on the Riemann surfaces, it means that we have for the cylinder, we associate to cylinder an operator that we call propagator. So it depends on T. And basically, it's a quantum mechanics with a circle action. So, of course, it's topological. Okay, higher topological. So we may say that we have Hamiltonian, and this Hamiltonian is exact. So Hamiltonian corresponds to translations in T direction.
And is there some kind of, I don't know, explicit example of such family of omegas? I mean, it looks like some correlator which in the limits only wants to be non-zero when points collide.
When points are close to collision.
Yes, yes. Mm-hmm.
Okay, unfortunately, so let me tell you the truth. Unfortunately, this is kind of reasoning.
Mm-hmm.
But your answer about examples is valid. So we already discussed. So we already discussed two examples. But I would not like to say explicit examples. Two indications of examples. Okay? Mm-hmm. So let me explain what I mean. First kind of example was the so-called B modulus. So we, in this course, studied the correlator and found that when we have large radius limit, that finite moduli part tends to 0. We did it explicitly. I remember that we were writing green function, looking for behavior of correlator, and we found that in the large radius limit, it means when the metric with the lower indices goes to infinity or metric with the upper indices is going to 0, the measure pointwise tends to 0. Pasha, do you remember that we computed that?
Actually, no. Well, I'm sorry. I'm just trying to remember. I think we mostly spent this course discussing a model, and
yes, but you see here, yes, but I'd like to remind you that we studied the B model too. Namely, we studied the structure of operators in B, observables in B model. We discussed behavior of correlators. So let me think.
I'm really blanking out. It could be on, I don't know, one of the seminars that that I was not on, but yeah, I really don't remember this.
Okay. Okay, so there is, so maybe we need, maybe at some moment we will come to this. Okay? So I'm thinking. Okay? There is a second. So actually, it is just the case, it was studied by BCOV. Exactly this case. So second example is the A model in tropical limit. So in tropical limit, as you see, the correlators are coming from the tropical graphs that are coming through cycles. So as we discussed, if something is non-degenerate in tropical limit, it is degenerate in string limit. Because finite position in tropical means degeneration in string. And actually, we will discuss mostly this. Okay, so okay, still I'll discuss construction. By the way, creators of BCOV were not very explicit about how to define correlators. And the statement that correlators vanish in the finite piece came later on. By the way, Donald, do you remember this discussion that we had?
Yes, I do remember the discussion, but I'm not sure we had it in this course. So I remember that we talked about correlation functions in B model and that it seems that everything is 0 in this limit.
Okay. So so maybe it'll be good to come to this topic later on. Okay. So I'll explain it in the following way. So first I'll show a set of axioms, and then I'll explain how differential forms on Calabi-Yau manifold fit this set of axioms. Okay?
Mhm. So first motivation, and then axioms. So consider such a vertex. From the string theory point of view, it is an operation 2 to 1. That is homotopically commutative, supercommutative, and associative. So in the set of axioms, we would demand that it's not homotopically, but it is actually supercommutative and associative. Second, there is a Q that is that together with M2 forms differential graded algebra. Now we come to the very important additional ingredient here. This additional ingredient is the operator G naught minus. The So as it comes from string theory, Q G naught minus anticommutator should be L naught minus. A rotation of the loop. However, in these axiomatics, we would prefer to restrict to states that are invariant with respect to rotations. So it means that Q G naught minus would be considered as 0. So the last thing, it is interesting to see how this G naught minus is related to the multiplication. So we demand that G naught minus is the second order operator. So several comments are important.
the notion of order of operator comes whenever you have supercommutative associative algebra. In particular, if you have supercommutative associative algebra, you may ask the following thing. You have, so let me comment the notion of order of operator. So derivations of the algebra A are first order operators. Now we would like to understand what is the second order operator. Always second order if the following happens. Suppose you have an element A of the algebra and the element B. So let us see how O, being second order, acts on B and A.
You mean on B times A?
On B times A. Ah, yes, of course. So actually it acts like this, plus it acts like this, plus it acts somewhere in between. So the notion of the second order operator is such that its commutator, so it's maybe the best way to say would be the following, that O, that action of O and B considered as multiplication. This commutator, actually supercommutator, is a first order operator. And actually one can go on and on. However, there is also another way to write it down without using notion of the first order operator. And this is called the 7-term relations. So let me discuss what is the 7-term relation, and then check and then show how second order operator are compatible with the 7-term relation. Okay? So before I'll describe it, let me recall that to be a first order, to be a differentiation is a 3-term relation. to be differentiation means so D applied to a product, and here we have a product once. So how can I say? Okay. Or equals. So this is to be a differentiation. Or it's a Leibniz rule. Now let us look for the similar thing that contains 7 terms. So why I call it 7? You see, in this definition, we use M multiplication only once. Now, when we are going to describe second order operation, we will have to use it twice. Okay? So now let us have a look at the graphs that we can potentially write. So I'll call this G2. Okay, I'll call it O2 in order to avoid the unnecessary associations. So how does 7 come up? We will use multiplication twice. So we will have 4 terms of this type. So actually, since multiplication is commutative and associative, we could replace this by a single vertex. So actually, these 4 terms is something like G, A, B, C. Okay, minus G, A, B, C, minus A, G, B, C, etc. Okay, minus A, B, G, C. So these are these 4 terms. However, there are also 3 terms. In 3 terms, I cannot contract this to a single multiplication. And then they look like this. So here we have 3 terms. And the condition of being the second order operator means that this 7-term relation holds. For any inputs. So let us make a test to see if it's correct or not. Is it what we assume by the second order operator? So just imagine that we consider second order operator something like D1, D2. So imagine that we work for polynomials. So it's a test. Let us think about such operator. So by D1, D2, I take two derivatives. And by f, I take some function. So let us make a test. Let us apply it to A, B, C. Okay? And let us see what's going on. So, of course, these derivatives could go to A, and so if they all go to A, to B, and to C, we have this first 4 terms. Plus, etc. Okay? Now, let us assume, let us try to see what else do we get. This 1 and 2 could go to 2 terms out of 3. Okay? But this term, so you see, here we have second order. So it means that one of the term is not differentiated. Okay, maybe it's better to put it this way. One of the term is not differentiated because these two derivatives could act only on 2 elements out of 3. And that's why I have these 3 terms. This, and this. Pasha, is it clear?
I think I did not understand your explanation, but I understand why this relation works.
And how do you understand why this relation works?
Well, I did not understand this arithmetic with, well, how I understand that it works, just because, well, you write the defect of the first order Leibniz identity and you impose that it's a biderivation. Then you just write trivially the seventh term identity.
Okay, so in any case, there is a 7th term identity.
Yes.
So, okay.
Now here I got lost actually in how you were distributing the derivatives. So, but
You see, here I'm just here. I have two derivatives. I have to distribute them among three inputs.
Andrei, I'm missing first of all what are the dot on the first line, and second, in the second line, whether the derivative acts on the product or just on B. Because
So
if the,
here, maybe here it's a misprint.
no, actually it was not a misprint. It was fine.
So here derivative acts on product, and here derivative also acts on product.
No, I understand everything except for your example. Because in the example, I don't understand what was dot 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 and what was.
Okay, so in this example, okay.
Okay, but is it any different from what you wrote on the second line? Or did you mean that the derivatives act on the product? But then one of the terms is already in the first line.
So so here both derivatives are acting on the same element.
Yes.
So there's no mix of first derivative, first order derivative. Like the product of partial 1 to A, partial 2 to B.
Well, there should be. I mean, the seventh term relation involves such objects.
Okay, so let us try to help me. Okay. So this is the seventh term relation. So maybe I'm confused in this example.
Now, okay, so seventh term relation, sorry, it involves, okay, it involves our second order operator acting on the triple product, the single products, and the double product. So you have the triple product and kind of just acting on single elements in the first line. So you should have action on double products just products in the second line. That will correspond to your three terms. So there should be, okay, so there should be A times the operator of B times C.
So I think that when I do like this, here I still have two differentiations acting here, two differentiations acting here, and
yes, exactly. So it's just there should be brackets in the second line. It's of bracket BC, of operator of B times C.
okay. So let us take a break. Okay. So I'm sure about relation, but I am.
No, it's clear how it works. And what you wrote is correct, except you should put brackets around B and C on the second line. And two more terms like this. Yes, exactly. And two more terms like this. So B times same stuff of AC and C times same stuff of AB. And then it's correct.
So what bothers me is that here there should be some cancellations between these terms and these terms, because already
cancellations will be if we expand the left hand side of the relation. And of course there should be some signs if you are worrying about cancellations.
yes, but moduli too. So
yes, yes, then you should expand the left hand side.
So here two derivatives x on A, two
Yes.
derivatives x on B, two derivatives x on C.
Yes.
Now, so now, when I'm writing here this thing, I have similar things like this, but twice.
Yes, but there would, with appropriate signs, it would be 2 minus 1 equals 1.
Yes. So that's what so with appropriate signs.
Yes,
So
with appropriate signs, of course, yes.
that here. Okay, so still you see.
But for instance, you will have like from the next to last term, you will have two derivatives acting on A, and from the last term also two derivatives acting on A. So
Yes, so it means that these should be with minus sign.
if they're all even, then yeah. But
Yes, if they are all even,
yes.
because here I will get D1B, D2C. Okay. So I'll have this term twice. Okay. And it would be, and one of them would be cancelled from the term like this.
Yes.
Okay, now let us have a 5-minute break.
So, Andy,
Yes.
is there some way to see kind of geometrically this relation? I mean, it says that there is a relation between rotating these tubes and it's a relation between the vertex, which is this, I don't know, like a sphere with 3 holes, and rotations of on the boundary 3 circles.
Yes. So it's possible to see it from the two-dimensional conformal field theory that is behind it. Let us try to see how it comes. So in rotation, we study the second order pole.
Right. Oh, okay. Okay. Yes.
So we look for this G dot. So it means that we do the following. We take this vector field here, V of z equals z. And integrate. So this is G naught.
Yes.
Now, what can we say about, so if it is derivation or not? So first of all, why Q is derivation? In conformal field theory, because we take
Counter switching.
yes, 1 second, but here we look to the first order pole. Or you can call it G naught, or you may call it Q. That's why here, if you have two, O1 and O2, you may have a look at expression that is G of z integrated over the contour gamma. And when Z1 and Z2 come together, you have the application of the G, yacht of J over the product, or this contour could be separate, could go into the product of two contours. That's why, because of this contour argument, it's a derivation. Now here the difference is that we have this Z. So what if we try to repeat the same argument? Namely, take O1 at 0, take O2 at some point W, take G at some point Z, multiply by Z, and integrate over the contour. there will definitely be the term where everything acts on O1. There will be term where everything acts on O2. However, in this case, we will have to replace this Z by Z minus W. So there would be one more term left. D of Z, say W, integral over gamma, O1 of 0, O2 of W.
So now you're thinking of gamma as encircling both.
Yes.
Oh, yes, okay.
And I definitely have an extra term. And this extra term comes from the first order pole. Suppose that G of Z has a first order pole with O1 and O2. Then it will be this pole. It is about the second order.
Sorry, I got lost.
So when we have this formula,
no, so far I don't know where this formula comes from. We start with something understandable.
okay,
Yes, so I understand the formula above.
from this.
Yes.
Now let us try to extract from this expression G naught acting on O1 and G naught acting on O2.
Yes.
So when I put it this way, I already have G naught acting on O1. So if there will be no contractions with O2.
Yes.
So this term is here. Another term would come let me see. Another term would come if the contour would surround W. However, if the contour would surround W, I will actually have two terms. First term comes from the second order pole between G and O2. However, here I have this Z.
Okay, I see. I see. Okay.
So let us make a typical integral, a model integral. So model integral would be that that involves the pole of G of Z with both 0 and W. And if I have Z here, this term would give me a contribution.
What?
So just imagine that I have the following product expansion.
Mhm. Mhm.
Something that contains Z minus W 1 over Z. I want to put Z upside. So this term also contributes. So here I can have this term, I can have term like this, and I can have term like Z minus W squared. So the claim is that all three terms contribute.
Mhm. Mhm. Mhm.
So when I multiply by Z, all three terms would give contribution.
Right.
So this term gives rise to G naught applied to O to O1, 0. This term G naught applies to O2, and then I take a product. And this term is a mixed term.
Mhm.
To get such term, you see, I have to have contraction with this field and that field.
Mhm.
Now, I want to impose one more condition. And this condition is that G naught minus commutes with homotopy that contracts Q to its cohomology. So under this condition, I'm sorry, I have to put one more condition, last condition.
Does this homotopy have anything to do with G naught plus?
You may say that G naught minus and G naught plus commute.
But is it the same condition as above?
Yes.
Mm-hmm.
Well, so it's not last. It's this is equivalent to such condition.
Mhm. Mhm.
So having all, so actually, this is the structure of super commutative DG algebra enriched with G naught minus. And the last condition will be cyclic. So there will be a pairing. It will be possible to work without pairing, but with pairing, it would be even better.
So an algebra enriched with G naught minus satisfying this condition 4 is called the BV algebra, right?
Yes.
Mhm.
So here, important thing is the compatibility of G naught minus with homotopy. So if you have algebra enriched, it is BV algebra. But here I demand more.
Yeah, yeah. So it's, yes, some additional datum to contract this algebra.
Yes. And with this data, I can write down Feynman diagrams.
But by the way, what do you want from pairing?
So what do I want from pairing? I want from pairing should be invariant with respect to both Q and G naught minus.
So the homotopy is generated by G0 plus.
So I do not demand the pairing to be related to G0 plus, only these two. Moreover,
So, okay.
It's probably also, there's compatibility with M2, right?
pairing.
Yes. I mean, is it not a cyclic structure on a DG algebra? So then there should be.
Yes, you are right. You are right, of course. And also pairing, of course, should be compatible with M2. Yes. Sorry, because the pairing should give a cyclic structure on DGA. Thank you. So it means that if I have a multiplication and if I have a pairing, then this should be cyclic. So when I say pairing invariant, it actually means, so I actually mean the following. So okay, No. So yes, it's enough. So it is the cyclic structure on the DGA, yes. So they should be cyclic too.
So what is operator corresponding to homotopy?
So I'll say what is the
So it should be G naught plus divided by L naught plus.
yes.
Right, right. But now you see L naught is generated by commutator of Q and G plus.
So homotopy so it means that when I think that I am integrating over the moduli of tube, once again, there is the length t and there is an angle phi. Then in conformal field theory, I associate to it
Yes.
G plus. So now I say G naught plus dt G naught minus d phi. So when I integrate over phi, I get invariant states. When I integrate over t, I get exactly G naught plus over L naught plus. Now, immediately, I want to give an example.
Sorry, you said that integration over phi you get invariant states, but you also have the G naught minus factor left.
Yes, yes, yes. So I'll get, of course, G naught minus also. So actually, okay, so you may call this homotopy. However, to the cylinder, I associate not homotopy. But actually homotopy times G naught minus. And this is the main difference between BCOV theory and say Chern-Simons theory. It is the type of propagator.
The time integral over T could be from epsilon to big L.
And here, Professor Hu says that that what I'm writing here is a bit formal.
Because of zero modes of the denominator.
No, so it's formal. So first of all, if homotopy is compatible with G naught minus, it means that there are no zero modes. So actually there is no problem with infrared. Because G naught minus, so when I say compatible, it means that G naught minus.
By zero modes, I meant zero eigenvalues. Zero eigenvalues.
Yes, of course. G naught minus annihilates
Okay.
zeros of L naught plus.
Mhm.
Now, another thing. Another thing is that there could be ultraviolet problems. So when Professor Hu said that we have to integrate between epsilon and L, so I explained that there is no problem where L is going to infinity. If homotopy is compatible with genus minus, because homotopy projects out zero modes of L naught plus. So homotopy is this on the complement. Of L naught plus zero modes.
Mhm.
But still, there are problems when I try to integrate, when I try to put this epsilon down to zero. It is because in some cases, in some, actually most cases, multiplication is not of trace class. So what could be this? Or this. So such thing could diverge. So now I'll explain construction assuming that there are no divergences, or they could be eliminated, or I'll consider so-called classical story. That's why Professor Hu wants me to keep here epsilon. But nevertheless,
Does one actually have divergences? Let me see. What am I trying to say?
potentially yes.
So things like conformal invariance or TCFT property do not prohibit divergences?
It's because here we are considering so-called field theory limit. So it's not computation done inside the string theory directly. It's a field theory motivated as a limit of the string theory, and since
so since we're killing that circle, an ultraviolet problem can arise. That's what you're saying.
yes, so ultraviolet problem would not be a problem if we would have a perfect string theory that goes down to this field theory. However, for the general model, it's not true. It's not known. I'm not saying it's not true. I say that it's not known. Actually, Actually, there is a problem, and I think it's unsolved problem, to construct B model as a string theory that I explained. And the origin. So I'll come to this. So maybe first I give an example, okay? And then I'll come to problems. Otherwise, it will be unclear why I am discussing problems of something that I have not explained in example. Okay. So having this, okay, BV algebra, etc., you can construct amplitudes in the following form. You consider trees, you consider graphs. You put M2 here. To propagators, you put H G0 minus. And so on. So at the tree level, it is something like this. So here I just drew 4-to-1 amplitude. Example. But actually, so these are loops. So you see in the loop, so loop is strangely oriented. So because of this orientation of the loop, I have to use pairing. For a loop, you have to use pairing to change the order. So in particular, here you have one incoming and two outgoing. So here we use this pairing. In the tree level setting, you may study both setting with pairing and setting without pairing.
You could have considered a loop with only two incoming arrows, and then you wouldn't need the pairing, right?
Yes. And you know this loop. So actually one can work with pairing and without pairing. With pairing, so without pairing, it would be our famous BF theory. And with pairing, it would be complete theory.
So
now
we really want, so G0 minus is really a part of the propagator.
Yes. You may try, okay, so let me comment. You may try to exclude G0 minus from the propagator. Namely, take it out of here and act here, or here. So then, remark. Taking G0 minus out of propagator would lead to the new vertex. I put it in brackets because M2 is not an operator. So it's a measure to which M2, to which G naught minus is not the first order operator.
So that's the Poisson bracket.
Yes. But you may see that you have Poisson bracket here and here, but you do not have it here. You still have multiplication. So it's impossible to write everything in terms of Poisson brackets only, even in oriented case. At least one vertex would come without this commutation of G naught minus and M.
So G naught minus commutes with H, right?
Yes. And this inability to write it this way is parallel to similar expressions in one-dimensional quantum mechanics, where you actually have the same structure. So there were operators that come here. You could take G naught minus and commute with one of the operators. Or even with two of operators. But number of operators is at least one bigger than the number of G naught minuses. So you need both. Now let me come to description of the original BCOV model. So BCOV model, original. So this should be called BCOV-like. Or maybe, so I call them co-Hodge, but maybe people would better understand them if I call them BV models. Okay. So BCOV example. Suppose I have Calabi-Yau manifold. With Calabi-Yau manifold, I can identify a space that is either the space, I'll call it V omega, that is the space of PQ forms, or I can write the space that I'll call VP. It is P polyvectors with values in 0Q forms. So when I use forms, I call this space V omega. when I understand it as polyvectors, I call the space VP. They are isomorphic. And the isomorphism is given by non-vanishing top form. Top means D not form. So this isomorphism is given in the following way.
So, I mean, this isomorphism switches between P and D minus P.
It identifies this and this.
So PQ forms with D with
So this isomorphism
with
takes
D minus P polyvectors, right? D minus P polyvectors valued in 0Q forms.
polyvectors valued in 0Q form.
Mm-hmm. Mm-hmm.
And the way how it is done is the following. Polyvector P corresponds to the form omega P. Done as follows. I contract the Calabi-Yau form. Maybe I will call it Calabi-Yau. And this is omega P. So how I do it in coordinates? Polyvector P is something that has indices. So it is P polyvector. So when I have P polyvector, I can form differential operation. On forms in kind of non-usual way, but so what do I mean by this? I want to understand PQ differential forms.
Mm-hmm. No, it's just a contraction.
Yes, as functions of dxi dx j bar. I would like to consider them as odd coordinates. So I can have such differential operator. So in components, it means that if I have P, then omega P is EI1 IP, and also it is J1 bar, JQ bar.
Oh, I thought we are taking the only holomorphic polyvectors. No?
No, of course, no. For the vectors taking values in, you see here was PQ.
Yeah.
For the
Ah.
vectors taking values
Ah, sorry. Yes, right.
in 0Q forms.
Mm-hmm.
So, and I have holomorphic indices. So I can track these indices.
Andrei, sorry, I'm still confused. Above you say P polyvectors or P comma 0 polyvectors valued in 0 comma Q forms. That's not the same as P comma Q polyvector.
Polyvectors taking values in 0Q forms
Is not the same as P comma Q polyvectors, right?
of course. So, okay. So when I say PQ polyvectors, I always mean the same thing. Maybe I sleep.
Okay, so then those indices should be downwards. The anti-holomorphic indices should not be the upwards.
Okay, taking values in 0Q forms.
Right.
So I'm always talking about this.
Then the anti-holomorphic indices should be down, right?
Right. So it is. Thank you. Of course, I should be down. It's a misprint. So I can track these indices. So when I do contraction of indices, it's some operation. But in order to understand the meaning of this operation, I just want to say that polyvector, that I treat polyvector, of course, as such operator. So when polyvector is acting on forms, it is the same. Now, so I have VP identified with V omega. And I will change, and I will say in each place what I'm using, VP representation or V omega representation. So in V omega, so in all of these representations, there is the bar operator called Dalbo. It would be Q. In VP representation, there is multiplication. Now I need to say what is G naught minus. So G naught minus would be Dalbo in VQ representation. Okay? We all know that Dalbo in VQ representation looks like the first order differential operator. However, it is first order differential representation with respect to multiplication of differential form that we are not using here. And it's important to avoid confusion. Now we need to take this Dalibor and put it to VP representation. So actually relation between VP and VQ representation is given by so-called odd Fourier transform. Namely, take a form when I'll speak about the form, so when I say form, I consider it as a function of x bar, dx bar. And then I take a very specific kernel. I introduce theta, and here I introduce dxi. And I take an integral over all dx, but not, but not in the standard way. I consider these dx's as some odd variables psi I. And here I take integral d psi 1, d psi d. So this is Berezin integral. You see, I was trying to write it in terms of dx, but then I realized that it could lead to confusion of notations. And of course, here I also write psi I. And this Berezin integral involves, of course, Calabi-Yau form. Because I need to pick up the external power. And when I do this, I will get polyvector. That is a function of x bar, theta I with lower index, and dx bar with the upper index. So when I decompose, I will get polyvector that takes values in 0Q forms. And this Fourier transformation, odd Fourier transformation, so you may take it or you may not take it, allows me to do the following. I have an operator G naught minus that is D in VQ representation. So when I do this Fourier transform, I would go to VP and then here I have this D. Written like this. So in VQ representation, this Dalibor is the first order operator. Now, when I am doing this Fourier transform, it becomes second order operator. Because multiplication by psi goes into operator d over d theta I. That's why in VP representation, I have operator of this type. So it's a second order operator. Okay? But I want to understand things in VP representation. You see, going from between V omega and VP representation implies Fourier transform. And I once again say that while there is a multiplication operation on differential form, it's not the operation that I'm using in this construction. But main result is that I have this second order operator, G naught minus, like this. So this operator is also known as BV operator. Now the last thing here is that there is compatibility of G naught minus and Q and Q. Not only they anti-commute with each other, but also G naught minus is compatible with homotopy. So to see this compatibility, we have to go to V omega representation, where one is D, another is D bar. And due to Hodge theory, we know that D anti-commutes with homotopy. So this is the main BCOV example. And another thing, of course, is the pairing. So the pairing is a standard integral in the omega representation. Actually, pairing, here we need to put inside, so it's almost integral of omega 1 and omega 2. However, here we need to put I to the power p minus q. It's called while operator.
Sorry, what? How do we contract forms?
We take form. Here we have operator that on PQ forms takes value I to the power p minus q. Then we multiply by the second form and integrate.
Sorry, I the root of -1 or?
Yes, yes.
Mm-hmm. Mm-hmm.
Okay, so now I make the second break. Okay.
Sorry, actually, and you said that sorry, the commutation of del and del bar, you said that it corresponds to commuting with homotopy, but actually homotopy was related to G naught plus, and we did not discuss G naught plus.
Of course. Of course. So this okay, all right. So you are right. Here we have to choose homotopy. Okay.
Mm-hmm.
So as homotopy we use. So if we use this as homotopy,
mm-hmm.
then we know that non-normalized.
Mm-hmm. Okay.
And normalized homotopy.
Okay.
Is this. Then it's clear that the D commutes.
Mm-hmm. Okay.
And this is BCOV theory.
Mm-hmm.
On the so I explain the general steps and concrete example. So people.
So do you have a vertex? I mean,
Of course, vertex is multiplication on polyvectors.
okay. Mm-hmm. Okay.
So once again, so let me repeat. So there is a polyvector representation and differential form representation.
Mm-hmm.
So to define Q, so Q is universally defined as Dalibor. Multiplication is defined as a multiplication in the polyvector representation.
Mm-hmm. Okay. So this defines the Feynman diagrams for BCOV.
Yes.
Mm-hmm.
However, homotopy is defined with the help of differential form representation.
Mm-hmm.
So like G naught minus is Dalibor in differential form representation. It is something of the first order. It is a product that we are not using.
Mm-hmm.
But when we go to polyvector representation, it becomes the second order operator
Mhm.
that we know as BV operator.
Mhm.
So we see that there is this second order operator. Now, we would like to see if what is the homotopy. So homotopy is defined in the differential form representation, like this. And we know that it's compatible.
Mhm.
So this is the structure, this is the example of the structure of BCOV constructed by BCOV. However, they constructed it for some reason only in dimension 3, but it is the complete construction.
Mhm.
So you may construct it if you generalize the algebra of Calabi-Yau. Like you may do it in Landau-Ginzburg models. So not only in Calabi-Yau in different setting, but in Landau-Ginzburg models. You may do them in the generation of Landau-Ginzburg models like Saita theory.
Sorry, I don't quite understand what you're saying now.
I'm saying the following. Suppose I have this structure. Suppose I have something like non-compact Calabi-Yau manifold.
Mhm.
And moreover, I can add superpotential.
Mhm.
This theory behaves in a way similar to Calabi-Yau.
I see.
Namely, you may also consider differential forms, polyvectors, everything in the same way.
So the whole Hodge package somehow deforms by the superpotential.
So to have the whole Hodge package, it is better to consider this.
Mhm.
Put here prime, then you have the full Hodge package.
But wouldn't we have problems with things that were commuting before doing this will stop commuting after doing a deformation?
So the only problem here is that this is not the second order operator. It has a multiplication. However, you may consider limit t bar tending to 0.
Mhm.
And this limit seems to be regular.
In partial W, you also have the t times partial W.
So you may say that partial W has t as a parameter, but I want to keep this t and take t bar.
No,
to the-
t in front of partial W. Okay.
So if you wish, you can do this, but I don't want this t and t bar to be complex conjugate. I want them to be different. So it's interesting to note that you have a Hodge package where these two are different.
Mhm. Mhm.
Because
Yes.
the Hodge package actually depends on the potentials. These are superpotential. So I say that T2 bar should go to 0, T1 should stay fixed. Here we still have Hodge package. So Hamiltonian maybe would not be real. However, its spectrum would be discrete. Okay, now I need to make a 7 minutes break. So you see, the third model that is very interesting. You see, now I don't have enough time to explain it, unfortunately, and also it's hot here, and I don't feel very well. So I will say something about how in BCOV theory, so I will not describe the third model right now. I'll explain that I explained once, but now there are new people. I'll explain what are special coordinates in BCOV model. Okay?
So can I just ask one thing? So this condition in the original papers that Calabi-Yau is of dimension 3. So is it, I mean, is it good for like existence of Z gradient or something like that on the space of fields, like in Chern-Simons, that there's something good happening in dimension 3? Or is it just an arbitrary assumption?
No, it's not an arbitrary assumption. It happens because you may restrict yourself in dimension 3 only with the standard deformation of complex structures. Namely,
okay, yes.
Namely, so after I describe this, okay, I should describe the deformation theory.
So it is similar to usual Chern-Simons.
Yes.
Mm-hmm.
So deformation theory.
Mm-hmm.
So you know, we see that we have Q, we have M2, and then and we have this G naught minus, or you may call it delta BV. It's the same.
Mm-hmm.
The equation is the following. How this theory could be deformed. And actually it could be deformed in general in the following way.
Mm-hmm.
So once again, this is odd operator.
Mm-hmm.
This is probably should be even. So this is in P representation.
Mm-hmm.
So if we want to see it in Q representation, we could, okay, so here is polyvector field, but okay, in P representation. However, this formula is algebraic in nature. So it is about operators that apply and commute in different orders.
Mm-hmm.
That's why you could equally well look at it omega representation. So here we'll have this, and here you will have differential form that is associated to P polyvector.
Mhm.
So let us see some examples. First of all, just imagine that this is d bar as we started.
Mhm.
Just imagine that omega p is a function. Then it's clear from this representation that we are doing such deformation. So it's example number 1. So it's called Landau-Ginzburg deformation. Now consider another example. Suppose that P is 1, 0 vector with values in 0, 1 forms. It is Beltrami differential.
Mhm.
Now let us go with this Beltrami differential where we can still work in this representation.
Mhm.
So here, mu ij is such a thing, such an object. Then I also have in this representation, by the way, it's such a thing in all representations. So what's important is that to compute the commutator of delta BV with this here or here. So in this representation, in representation of actions on forms, I will write it like this. Now, I would like to commute. So in this representation, in the omega representation, Beltrami is the first order operator. And Dalbo is also first order operator. So I would like to commute them. And actually, there will be two terms. One term is when differentiation is acting on mu, and another term where this acts here. So if I assume that mu is transversal, namely di mu ij bar is 0, then this commutator would give mu ij bar dxj bar do dxi. So I'll erase a lot of things. And Q deformed would be d bar plus mu ij bar dxj bar du over dxi. So this would be d bar mu. So it means that this formula actually gives deformation of complex structure, or with the function generalized complex structure. So I explained it to the first order. However, in general, one has to solve Bauer-Cartan equation that is also known here as Cadayero-Spencer equation.
So what was the role of this transversality condition? So if we don't satisfy it, then we don't get a deformation of a complex structure?
Yes, so we need to use transversal. So that's how it looks. At the moment, I don't quite remember what happens. Could we get rid of it? Or maybe I missed something, but
So that is the
maybe. So I consider
the Morrow-Cartan equation is the integrability condition for deformation.
yes, of course.
So in principle, P could be any polyvector or higher degree forms.
Yes. So the equation is the following. So I prefer to. So you may prefer to call it delta BV. Okay. So I'll write it in terms of delta BV. So this deformed thing should square to 0. So we'll have a condition QP okay, so let us compute it. So since Q squares to 0, all this is delta BV applied to QP plus this. So our Cartan equation is when we demand that this goes to 0. So in the case of of deformation by f, it's always like this. In the case where we have Beltrami differential, for Beltrami differential, it is this integrability condition. Here brackets are brackets as vector fields. Actually, this bracket structure comes from this structure. Because when you consider this BV applied to P, you are producing a vector field that corresponds in the master equation to the field P, and then you have this BV commutator. So let me be a bit more explicit. Delta BV is d over dxi, d over d theta I. Imagine that P is some function of x bar, dx bar, so they would not be involved in computation. And also, x is important. And if it's a vector field, it has the following theta dependence. So in particular, Beltrami is here. Beltrami is term linear in dx bar. Then, what is delta BV on P? It takes one over d thetas and makes it a vector field. So the structure would be like VI d over dxi. And when you commute it with yourself, you will get the bracket like for vector fields. So you may check that it's like this. You see, it's too hot here, and I'm a bit tired, so I cannot work out the computation on the board right now. I'm sorry. And it was this in complex dimension 3 that was reproduced by PCOV. Because they never knew about higher deformations, and they were not considering non-compact cases.
So
Now-
I have a questions.
Yes.
So if you put not the Beltrami differential, just functions, which is the solutions of Morocco-Tan equation.
Yes.
I mean, holomorphic functions.
Yes.
Then what do we deform in this case?
It is so-called generalized complex structure in sense of Barannikov-Kontsevich.
Oh, yes, yes.
We are deforming this to this.
Oh. We're just deforming differential. Okay.
Yes, we are deforming differential. So here, important thing is that previously people were thinking about so-called geometrical complex structures. When you have a tangent bundle and you complexify it, and you find the almost complex structure, you look when it's integrable. Later on, story went as follows. First Witten in 93, or maybe at the same time, 93 or 94, studied fields in B model. And he found, so everybody found it, that they are polyvectors with values of differential forms, of antiholomorphic differential forms. So he asked the question, what does it correspond to? Because formally on the algebraic level, you can use all elements to do deformation. However, only one particular class of elements, namely Beltrami differentials, were identified with the deformation of complex structure. After that, people had to admit other fields to be equally valid as deformation of the generalized complex structure. And then people realized, look, we saw such things before in Landau-Ginzburg story. It is this deformation.
Sorry, I missed what you said. Why? I mean, these deformations are fine, at least that they don't, except that they don't preserve the degree of a form.
Yes, they don't preserve the degree of form, but they were not deformations that people studied before.
Mm-hmm.
Before all this business, people studied only so-called geometrical deformation, namely deformation made by precisely Beltrami differential. So it was the structure. It was what happened in the business before. People studied deformation of complex structure on the smooth manifolds, and they of course found, and that was exactly the content of Kadeira-Spencer theory, that they are given by Beltrami differentials that satisfy Maurer-Cartan equation. So it was an old standard theory. Now, then people realized that it is better to redefine this notion, because algebraically, these Beltrami differential are not that distinguished. They should be considered on the equal footing with other deformations of lower degree and of higher degree. And since then, people study general deformations.
So what are the most general forms of deformation?
So the most general form of deformation is, of course, what I have written right now. Q plus delta BVP, where P is polyvector with values in 0 Q forms. And in many cases, you can take you may say that the most general is d bar plus this. So pick up some complex structure and add. So this is generalized. And it is this structure that is used in say for Calabi-Yau manifolds. Also, the Landau-Ginzburg model. Where we have this. You may ask, could we put this F here inside? And so formally, yes. However, it is a big deformation. If we put this F to 0, we would drastically change cohomology of the theory. So you may speak about small deformations and big deformations. So this is perfectly well for small deformations. However, for non-compact case, it's better to keep here such df naught. Or if you have non-trivial topology, you may put here things like this. So here you have D closed one form. And also D bar closed. So it is the most general case. Since this D closed and D bar closed one form could be 1,0 form, could be in cohomology, it could not be written like df. So you have to keep it from the very beginning. And then the deformations would be like df plus some other deformation. But such deformation, the change of this D closed 1,0 form is not a deformations allowed in this way. So it is tricky. It's a tricky thing. So periods of this 1,0 form is a moduli of the problem. However, in the rest of deformation, there is a special structure. And the appearance of this special structure is like this. Under conditions that mentioned above, one can show that such operation so here I have sum over threes actually solves Maurer-Cartan equation. That's first thing. Second thing is that such solution are non-linearly parameterized by cohomologies of Q. because not only it's a solution, this solution also comes with very particular parameterization. And it means that we have special coordinates on the space of solutions. Okay, so let me answer a question and let me quit because I'm a bit tired. It's too hot and I don't feel 100% well.
Thank you. Yeah, I think I'm not having questions.
So we will continue next time. So see you. Goodbye.
See you. Mhm.
Thank you.
Thanks a lot.
Yeah.
Okay. See you. Bye bye.